Hardware or software? Code or gates? Performance or flexibility? Power or area? Fast implementation or complex engineering? Finishing your design or getting fired? Okay, wait. Forget that last one. It's a question for the ages, particularly this age. One of the fundamental things we have to consider for each part of our design is whether to implement it in software or hardware, or best case, a little of both. In applications like video, the trade-off between hardware and software is critical. Hardware implementations can be considerably faster and more power efficient, but at the cost of components and design time. Software brings the power of flexibility and rapid implementation, but suffers on the performance and power side. Making the right trade-off in your design can be tricky without the right platform to evaluate your options. Hi, I'm Amelia Dalton, host of Chalk Talk. Today we're going to talk to Todd Kelling of Altera and Troy Jones of Macnica Americas about using Altera SoC FPGAs along with hardware and software IP, the DirectFB library, and the ever so awesome Helio View kit. We're going to demonstrate the power of Altera's FPGA SoC architecture, which allows us to try our hardware-software trade-offs with some serious video rendering. And before we get started, remember to click that link. There you can register for Macnica America's 2014 V-Workshop Series for the Altera SoC. Hi, Todd. Thanks so much for joining me again.
Hi, Amelia. Yes, it's great to be back.
And welcome, Troy. Thank you so much for joining me today.
It's a pleasure. I'm glad to be here.
So, Todd, we've talked before about SoC FPGAs, and it's been about a year, I think, since we talked last. Can you refresh my memory about this new kind of product?
That's right. We spoke about this new class of device which combines the ARM processor plus an FPGA and why someone might want to use it.
Sure, yeah. So, Todd, how's it going with this?
Really just fantastic. It's really exceeded our expectations. We've shipped over 6,000 development kits in the first 9 months.
Awesome.
And we've had nearly 3,000 customers in hands-on workshops worldwide in 2013, including people driving from Atlanta to South Florida just because the local one in their backyard was sold out.
I love it. That's great. So, for those of my audience who might not have seen your first Chalk Talk, give us an overview of the architecture and some highlights of these SoC FPGAs.
Sure. We've got basically two parts of the chip. We've got a dual-core ARM processor along with the FPGA fabric.
Yeah.
You'll see that on the right in this diagram. And that's going to extend depending on what chip it is. But it's not enough just to slam these two chips together. It's got to have a very high-speed bus between the two such that that doesn't become the bottleneck.
Right, yeah.
And so you can see here with our Altera SoC FPGAs, we've got multiple buses between those two halves of the chip, giving us over 125 gigabits per second interconnect.
Wow, okay.
A couple other key things are the access to the memory. The FPGA can go through the hard processor system up to the memory itself, the HPS memory, or we have separate memory controllers also available just for the FPGA. So it can use whichever fits the design best.
Very cool. All right.
And last but not least is data integrity. We want to protect the data throughout the system. So we've got ECC on the memory controllers up to 32-bit, ECC on the L2 cache, the flash data RAM, things like that, and even some of the peripherals, such as the Ethernet controllers.
So, Todd, what application areas are you seeing this go into?
We're seeing people design these products into multiple segments and many exciting applications. Things such as industrial drives and PLCs and HMI, the human-machine interface, as well as automotive, wireless and wireline communications, broadcast video, medical imaging, just about everything.
Okay, so when we talked a year ago, we knew people were going to do some seriously awesome and cool stuff with this technology. So let's bring in Troy from Macnica to talk to us about some cool and awesome stuff people are actually doing.
Okay.
So, Troy, before we jump into talking about graphics, video, and FPGA SoCs, can you tell me a little bit about Macnica Americas? Who are you guys? What's your deal?
All right, not a problem, Amelia. So Macnica Americas is an Altera distributor that focuses on the engineering support to help engineers like yourself develop their products, from IP development, product selection, or a full-featured design assistance and distributor, if you will.
Very cool. Okay. So let's dive in, Troy. You guys have a cool application for this technology. Tell me about it.
So what we want to talk about today, Amelia, is graphics rendering and video processing using these Altera SoC devices that Todd spoke about just a minute ago. What we really want to showcase here is why some of the architecture actually matters in these implementations.
Okay, cool.
So what I want to talk about, there's actually 3 different phases or 3 different implementations I'm going to cover today. We're going to talk about some software-specific graphics rendering.
Okay.
Then we'll switch gears and talk about a hardware-only implementation.
Cool. Okay.
And then, hey, let's take advantage of this architecture with hardware and software sitting next to each other, and I'll show you a demonstration of a combined hardware-software solution.
Fantastic. So what is it in this architecture that makes this stuff work?
As Todd spoke, there's extreme flexibility with these SoC FPGAs. For instance, there's the dedicated hard memory controllers, both on the FPGA and the HPS side of things. But probably the biggest feature that we want to take advantage of here is the FPGA fabric. Many engineers such as yourself are very familiar with a standalone processor.
Right.
Well, these SoCs give us the advantage of having customizable hardware in the FPGA fabric. So that's the flexibility that we gain here. A very positive side effect of that is performance. Okay, so now we don't have an SoC and an FPGA sitting left and right on a physical board. They're in the same chip.
Yeah.
So the communication between those two halves, again, give us the performance advantages that we need. And one additional feature is debugging capability. We don't have to have all these special hooks built into our board. They're built into the chip.
Right.
So in light of time today, we're not going to be able to speak to debugging specifically, but that is one advantage of these SoC devices that can be explored as well.
Okay, Troy, I think I understand this conceptually, but let's talk about some specific applications. That might help.
Great, let's do that, Amelia. So what I want to concentrate on today is specifically the interface of the FPGA to the HPS SDRAM controller.
Okay.
So if we take a look at the diagram here on this page, this is a generic representation of the HPS on the left side in the green, with the dual ARM9s as Todd talked about. We got our L3 interconnect. This is all the fancy stuff that makes it all talk to each other inside.
Yeah.
And then our SDRAM controller that goes off chip. On the right side of this diagram in purple, we'll see the FPGA fabric.
Sure.
So what we're going to talk about over the next few minutes here is that interface of the FPGA to HPS SDRAM specifically.
Gotcha. Okay. So you said the first application was a software-only implementation. Is that right?
Yes, you're right. So let's take a look at a processor-only implementation, if you will. So if you have a graphics implementation that is necessary but isn't going to be highly graphics intense, something that the processor has plenty of bandwidth to handle, then we can go with this is example demonstration here. So what we're doing here is we're actually using DirectFB. Now that is a open source graphics rendering library. We'll cover that more in just a minute. That's on the software side. The underlying hardware in the demonstration is going to be simply an LCD frame grabber with the LCD driver. So we're just going to grab frames and spit them out to the LCD.
Okay.
Nothing special is happening in the FPGA here. It's all done by the software. As you can see, the LCD frame grabber is going to grab its individual frames from the HPS SDRAM across that interface between the HPS and the FPGA.
Right. So, Troy, just a second. How exactly does the frame grabber receive its frame from the HPS memory space?
So, referring back to that first diagram I showed you, this particular implementation of the Macnica LCD IP using the DirectFB libraries is going to use a 128-bit Avalon memory mapped interface between the Macnica LCD frame reader and the HPS SDRAM.
Okay.
So this is our main pipe that we're talking about in this design.
Okay, that makes sense. So you mentioned this is a software-only implementation, and you mentioned DirectFB. I'm sorry, what is that? And how does this play with the hardware part of the solution?
Great question, Amelia. For those of us hardware engineers, this is kind of stepping into the software realm, and
Yeah.
not quite. Yeah, what is it? What is this software stuff?
Right.
So to sum it up simply, DirectFB is open source. That's good. It's free.
Yes.
Nobody likes to pay extra money. DirectFB is a thin library system that is designed specifically for rendering graphics in an embedded system.
Okay.
So the screens and the layers are produced by this library system.
Okay.
Some features of it are windowing, translucent displays. You actually have multiple layers as well. One other feature that we do take advantage of in this demonstration also is input device handling. So one
Okay.
thing that I didn't mention about this Helio View board is that it has a touch screen on it.
Cool. Okay.
So the touch screen is actually processed by DirectFB in this example as well.
Okay.
Now, one thing to draw attention to with DirectFB, it has the capability to do hardware abstraction. And what I mean by that is if the software isn't doing enough, you can actually implement additional hardware blocks to increase performance of DirectFB. Now, we're not touching on that today because I want to give you the example of software only.
Yeah.
Now, this can be accessed free of charge through www.directfb.org, just as the slide shows out here.
Fantastic. So we're going to do a demo here, but what's the bill of materials for this demo?
Good question, Amelia. What we're going to do today, through all of our examples, we're actually going to be utilizing the Impression Helio View demonstration platform and evaluation board. This has an Altera Cyclone 5 SoC device on it, as well as an LCD display.
Okay.
So for this first software-only implementation, as we talked about it in the block diagram, we have a frame grabber and an LCD driver.
Yeah.
And it also has a touchscreen controller. Those are physically in hardware.
Okay.
Now, on the software side of things, we're going to use the DirectFB core libraries, as well as some other common graphics rendering libraries, as you can see here on the slides.
Cool. Okay. All right. Well, Troy, let's take this baby out for a spin.
All right, let's take a look. We see here Linux booting the DirectFB libraries. The first demonstration are the penguins.
Hey, cute penguins.
You can see here that a nice smooth 60 frames per second can be achieved with a software-only solution. No hardware other than driving the LCD.
Cool. Okay.
Another cool one, this might freak you out a little bit, Amelia.
Uh-oh.
We've got a skull. So this is actually a very cool 3-dimension rotating skull. We can process the touches through the I2C controller that I mentioned, but all the frame rendering for the LCD display are done via the HPS processor.
All right, Troy, that skull is kind of freaking me out a little bit.
All right, so let's move on to one final one. This is serene. We've got a nice star field. Each individual item is being manipulated by the HPS processor. Again, no FPGA architecture is being handled here, other than the video frames are being handled from the HPS over to the frame reader.
Very cool. Okay, that was awesome, but that was just a software-intensive implementation. You said something about a hardware-only implementation?
You're right, Amelia. So the next thing, let's switch paradigm completely. Let's
Okay.
go over to the hardware side of things. In this Altera SoC FPGA, we've got tons of FPGA space.
Yeah.
Which is great at processing video streams. What we're going to take advantage of here is the Altera Video IP Suite. As you can see here, there's a huge grab bag of video blocks that we can use.
Looks like it.
So what we're going to do, if we take a look at this block diagram, this is the implementation for processing high definition video. There are several blocks that I want to draw attention to here that the demonstration is going to showcase.
Perfect, okay.
We've got the scaler. We're actually going to do some alpha blending.
Cool.
So that means I can give you some picture-in-picture.
Excellent.
I can fade your picture for you. It's some really cool stuff. Now, in this implementation, notice there's no ARM processor here.
Mm-hmm.
Everything is being handled by the FPGA fabric.
Okay.
Now, some smart engineers like yourself might ask me, well, wait a minute, there's got to be some control going on of these blocks.
Right.
You're right. there's a small touch of software here. The only thing is we're actually using a debug port to control the configuration of these video IP blocks.
I see. Okay.
Yeah, there's no operating system or anything magic going on behind the scenes.
All
We're
right.
just using a debug port.
Okay. That's cool, but I'm seeing a single HDMI stream here. Is that all it can do?
Good catch, Amelia. And that's one thing that's great about having our FPGA here. It's flexible and very powerful. So yes, we can bring in multiple HDMI streams. Maybe it's a VGA stream, maybe, different formats. It's flexible. That's the whole idea behind this thing. So no, this is simply one example. And the Helio View board that we did the demonstration on, we have a single HDMI input port.
Yeah.
Simply that's why.
Cool. Okay.
So Amelia, I want you to pay attention here and look. This is FPGA-based architecture, but we've got the HPS SD RAM in there.
Okay. Troy, I am paying attention. How does this differ from the other solution?
All right, great. So if we look at the next diagram here, got the similar blocks. We've got the HPS on the left, got the FPGA on the right. Here we have a similar, actually it is the same 128-bit memory mapped interface between the FPGA fabric and the HPS. However, all the video processing is done on the right side. The only thing that is going across that interface now is access to the shared SD RAM. The processor is not doing anything here. It's all the FPGA. So
Gotcha.
again, this is where the flexibility of our architecture really is showcased. You can access the memory that's part of the HPS in the FPGA fabric very efficiently.
That sounds cool. So what kind of video are you going to show us?
All right, let's take a look here. So the video IP suite allows us to process HDMI as noted in the block diagram.
Yeah.
So you can see here we've got a really cool video running. We can do scaling, so we can downsize. We can also do picture-in-picture. You can
Cool.
see the color bars in the background versus the live video up front. We also have the capability to do alpha blending, which gives us transparency.
Ah, cool.
So wait for it. And there we get it back. Okay. So these again are all features of the Altera Video IP Suite in FPGA Fabric, right? The processor isn't doing anything here. Okay. So you can leverage the power of the FPGA Fabric accessing the HPS SD RAM and get very nice fluid video processing.
Hey, wait. I was watching that. It's okay. So you showed us hardware and software. Do I have to pick between the two? What if I can't make up my mind, Troy?
All right. Glad you chose an Altera SoC because that's exactly what we want to hear. It gives us the ability to be flexible and switch
Fantastic.
between the two. So instead of having to build a board with a standalone processor, standalone FPGA,
Yep.
oh man, I made a mistake. Let me rebuild the board
Right.
because I want more functionality in my processor compared to my FPGA. You've got it all in one. So yes, you have the flexibility to do both. What I want to show you next is actually Android.
Whoa. Okay.
Yeah, I did say Android. Okay.
Wait, this is an Android running on an FPGA? I've never seen that before, Troy.
All right. Yes. So we actually have partnered up with a company by the name of Fujisoft, and they have created an implementation of the Android operating system running on the HPS dual ARM processors and actually using the FPGA fabric for some graphics acceleration.
Very cool. Okay.
So every single Android implementation that's out there has to have graphics acceleration engine with it.
Right.
The Android operating system is just so heavily graphics intense, there's almost no processors out there that can handle it standalone. So this is the perfect example of doing some in software and some in hardware.
Okay, cool. I'm excited about this one, if you can't tell. Show me how it works.
Okay, so in this design, the HPS, so the dual ARM9s,
Yeah.
are actually handling some of the simple frame processing. So what is simple in Android? Well, let's talk about some of the static menus.
Okay.
Maybe some of the icons, right? I mean, if you don't touch the screen of an Android, it just sits there.
Yeah.
So those static frames are rendered through the processor system.
Okay.
Now, on the other side of things, let's say you want to watch a video or you've got a video game that you're playing on your Android.
Yeah.
That's highly graphics intensive. So there's going to be a graphics accelerator handling that portion of it.
Gotcha.
So as you can see in this diagram here, we've got the ARM processor in there talking to its SDRAM.
Yeah.
We've got the purple FPGA blocks, again, driving the LCD display.
Yeah.
And then we have in the red blocks a graphics acceleration IP system. Now, this particular graphics accelerator is custom to Fujisoft. This is their proprietary graphics accelerator.
Gotcha.
But the thing to keep in mind here is that this is a shared architecture with the ARM processors handling some of the graphics rendering and the hardware handling some of the processing, sharing the same SDRAM interface, talking to a single LCD display.
Gotcha. Okay. So it's time for my usual question. How are we communicating with memory?
All right. So we've all seen this block diagram. The difference here is I'll call it the standard FPGA blocks in purple. In this implementation, the DMA engine actually uses a 64-bit memory mapped interface.
Okay.
Now, the secret sauce that Fujisoft has put in place for their graphics accelerator actually uses two 64-bit interfaces to that same SDRAM controller.
Okay.
So in this implementation, we have the ARM processors, the DMA engine, as well as the graphics accelerator, all accessing the single piece of SDRAM with very high efficiency.
Okay, wait a second here, Troy. Isn't Android a Linux implementation?
Aren't you a smart one, Amelia?
Hey.
So absolutely. This particular implementation is using Android 4.0, which is commonly known as Ice Cream Sandwich.
Yes.
Which is actually a layer on top of a Linux kernel.
Yeah.
This Linux kernel is Linux kernel 3.7, and this has all been ported over to the Altera SoC device. And then underlying are specific drivers for Fujisoft's graphics accelerator, the frame buffer driver, as well as other Android drivers, if you will. There are very specific Android drivers for this implementation.
Yeah. So it seems to me like some of the mojo here is how we're doing graphics. Can you give me some more details on how that works?
Yeah, if we can take a quick look at this diagram here, starting in the upper left-hand corner, basically an Android application wants to draw something.
Yeah.
So it's going to request a layer buffer. That layer buffer then is handled through the system server and the underlying Linux and Android libraries. So now the trick comes is when these layers have to be manipulated rapidly. Okay.
Right.
So we're now looking at the green block in the center of the diagram here. This is where the Android implementation makes the decision to throw these layer processors off to hardware. That's what's referred to as a surface flinger.
Okay.
So then these layers get handed off to the graphics accelerator, which then is passed on to the frame buffer drivers and then pushed out to the LCD.
Gotcha. Okay, so this graphics processing seems like a place where we might want to do some hardware acceleration in the FPGA fabric. Am I right?
Right. You have been paying attention. That's awesome. So in this implementation, we saw that those red blocks in the diagram were Fujisoft's graphics acceleration IP.
Yeah.
That's exactly why it is there, is to assist with the graphics rendering.
Okay.
If we take a look at this slide here, what Fujisoft has done is they've put alpha blending, image rotation, shrinking and magnification, as well as layer mixing into their graphics IP block.
Cool.
Now, they also put a nice little switch in there. You can simply turn it off.
Wow.
This is great because this is how I can show you the differences. So if we take a look at our performance with the graphics acceleration IP block turned on, we get some nice 55 frames per second.
Yeah.
Turn that switch off and our performance drops to 33.
Whoa. Okay.
So this is where, again, as the developer, you get to choose where am I going to spend the horsepower?
Right.
In the processor or in the FPGA fabric? Perfect trade-off.
That's super cool. Okay, let's bust out this Helio view again and see how this one works.
All right, this one's cool. This is my favorite demo.
Awesome.
Amelia, we can see Android is booting up here.
There it is.
We get to the common login screen.
Yeah.
All right, so let's go ahead and log into this machine.
Okay.
All right, and then first thing I want to do is show you some static menus, if you will.
Okay.
So this is going to be very familiar icons of an Android system.
Sure.
Okay. Let's look at some more graphics intense things. So in the demonstrations, let's take a look at rotating cubes.
All right.
Okay, so this is stuff that's being processed by the graphics acceleration IP and the FPGA fabric.
Gotcha. Okay.
Now this one, yeah, looks all nice and dandy, but we don't see any feedback of what is the quality.
Yeah.
So let's look at this sprite, rotating sprite.
Okay.
This is a common de facto standard for measuring performance. We can see here we've got a nice smooth 55 frames per second. That's actually done with OpenGL.
Okay.
And one final one, everybody likes the Rubik's Cube.
Oh, yeah. Come on.
So we can see very smooth, very clean, and this graphics processing is done in the FPGA instead of the processor.
Fantastic. All right, Troy, this is awesome. But I think I'm just dipping my toes in the water here. What about more information?
I'm glad you asked, because you're right. What we've talked about here today is just the tip of the iceberg. There is a lot of stuff happening under the hoods.
Yeah.
So what I recommend doing is taking a look at some additional training.
Okay.
So Macnica Americas actually offers some free online virtual workshops.
Cool.
So we're going to be starting these up in mid-March, and they are roughly 1-hour sessions where you can learn how to do these things.
Great.
It's really fun. If you have one of your own Helio View boards,
Yeah.
you can actually sit there and follow along with the instructors.
I love it. Okay.
So we cover everything from how do you turn the board on, how do I get Linux booting up, all the way through that Android demonstration you just saw run. So
Cool.
I highly encourage you to check out our virtual workshops. Highly informative.
Fantastic. Well, I think that's all I have time for since I'm going to go view one of your workshops right now. Thank you so much for joining me today, Troy. It was a pleasure speaking with you.
Thank you for your time. Thanks.
And thank you so much for joining me today, Todd.
Thanks, Amelia. It's been great being here.
Also, before we go, don't forget to click that link. There you can register for Macnica America's 2014 V Workshop Series for the Altera SoC.